Hi everyone, today's lesson in calculus is going to focus on two rules. Two rules that sort of merge into one. We're going to call this the chain rule and the power rule for functions. So I start off the notes here today by saying, suppose we want to differentiate the function y equals x to the third plus 4 all raised to the 100th power. Okay, I have two bullets here. The first bullet says, the power rule won't work because that rule only applies to finding the derivative of x to the nth. So see the difference? The power rule that we learned the other day is just a single variable x raised to the nth power. This problem up here is so much more than just an x. We're now taking x cubed plus 4, the binomial, to the 100th power. And this doesn't match this, so we can't use the regular old power rule. So the second bullet says this is where the chain rule comes in. So here it is, the chain rule. For differentiable functions, y equals f of u and u equals g of x, this right here is going to be our chain rule. So it says the derivative of y with respect to x is equal to the derivative of y with respect to u times the derivative of u with respect to x. Now, if you look at the math here, the reason we can say dy dx is equal to all of this over here is because if you cancel these du's out, you're right back to dy over dx. So you really have dy dx equals dy dx, but that would be if you canceled these du's out. But we don't want to cancel those out because we want to figure out a different way to write dy dx. So we're going to keep it like this. Okay, so now using the chain rule, watch how it pans out with example 1. So I just brought that same example from the top down. It says, find the derivative of, and here it is. Okay, so here's what I want you to do. Whenever you are doing like a quantity raised to a power, you're first going to identify y. Okay, so just leave a little space here. And we also have to identify u. Okay, now u is the stuff inside the parentheses, more than just the x. So like the stuff here, the quantity being raised up to the 100th power. So I'm going to let u be x to the third plus 4. And so what that does to y is now I can write y as u to the 100th power. Since this is u, y equals u to the 100th power. Now, I'm going to differentiate each of these individually. So if I differentiate y, this is going to read as the derivative of y with respect to the variable u. And what's great about this, by changing my function to u to the 100th, I can now use the regular old power rule. See, it's just one variable to the nth power. Well, now that I have u to the 100th power, that's one variable to the 100th, I know by the good old power rule that the answer to this is 100 u to the 99th. So I bring the 100 down to the front, rewrite the u, and subtract 1 from the exponent. Okay, over here, I'm going to find the derivative of u now with respect to the variable x. So the derivative of this equation with respect to the variable x, again using power rule, is going to be 3x to the second and then plus 0 because constants have a derivative of 0. Okay, so taking these two pieces of information and remembering what the chain rule says, we now know that dy dx is equal to, follow your chain rule up here, derivative of y with respect to u is right here, 100 u to the 99th power times the derivative of u with respect to x is 3x squared. Okay, and now the last step to this chain rule is to filter the u back in. So go back to what u was in terms of x, and let's get that back in there. So 100 times x to the third plus 4 to the 99th power times 3x squared. And if you want to, you could actually combine the 100 times the 3x squared and bring that all to the front. So maybe you write your final answer as dy dx is equal to 300x squared times x to the third plus 4 to the 99th power. That's going to be the final answer. Okay, now that is the true definition of the chain rule. Something that students have liked over time that I've said about the chain rule will come up a little bit later, like a little bit of a shortcut to this. But for example A and example B, we're going to go ahead and just use the official chain rule. So let's look at letter B. It says y equals the quantity 2x minus 7 to the fifth. And again, what signals chain is that this is a quantity, not just an x. So again, we have to identify what y equals and what u equals. Okay, so we'll let u be the 2x minus 7, the quantity that's being raised to the power, and then we'll let y equal u to the fifth. So differentiating these will give us the derivative of y with respect to u by the power rule is 5u to the fourth. And over here, the derivative of u with respect to x is simply 2. So taking these two pieces back to the chain rule, the derivative of y with respect to x, dy dx, is going to be, look up here, dy du, so that's this guy, 5u to the fourth, times du dx, which is 2. So filtering the u back in, I'm going to have 5 times 2x minus 7 to the fourth times 2, which we could then write, if we take the 5 times the 2, 10 times 2x minus 7 to the fourth. That's going to be our final answer. And just FYI, I'm sure you already know this, but just to remind you, you may not distribute this 10 because order of operations would say that we have to take 2x minus 7 to the fourth power first, then distribute the 10. And I don't really want to do that, so we're just going to leave our answer like this. Okay, so let's flip the page and read this little paragraph here. It says, as we use the chain rule in these examples, we start to notice a pattern. We can use the chain rule to establish the derivative of a function raised to a power, not just an x raised to a power. So I'm going to spin off the chain rule now and call this new simpler rule the power rule for functions. So if g is a differentiable function and n is an integer, then check out this rule. The derivative with respect to x of the function g of x is equal to, you know what, I made a typo here, hold up. That should really say the derivative with respect to x of g of x raised to the nth power. I forgot my little power there. Okay, that's better. So add an n right there. So what you do is, you bring the n down to the front of the quantity, you rewrite g of x, you reduce the exponent by 1, and then you multiply by g prime of x, the derivative of g on the back. This is like the extra link, get it? Links in chains, the chain rule, this extra link. So it is really the power rule from the old power rule, because we know to bring the exponent to the front and reduce the exponent by 1, then multiply by the derivative of g. So this is the extra part. Now look at how that worked over here. So we went through, look at all this work we went through to run the chain rule. What we notice is, look at this line. Let me highlight this. Look at this line right here. See how this 100, right, came down to the front. we rewrote the quantity, and we reduced by 1. See, that looks like the power rule. But then we multiplied by the extra link, which is the derivative of the inside here. See how the derivative of this is 3x to the second? Okay, look at the second one we did. Here's the original problem. Look at this line right here. So we brought the 5 down to the front, right there, rewrote the quantity, reduced the exponent by 1, multiplied on the back by the derivative of the inside. This is sort of a shortcut to doing this part. So by using this new power rule for functions, you eliminate having to go through this. Okay, but it was only by going through this that we realized this rule. So let's try to use this simpler rule, I guess, on the next 3 problems. So letter C says y equals 1 all over 4x plus 5 to the third. Now we could use the quotient rule on this, but I'm going to be a little bit more clever than that, and I'm going to rewrite this as the quantity 4x plus 5 all raised to the negative third power. So I'm going to bring this up to the top and raise it to the negative third. Now, could use the chain rule. I'm going to instead use this sort of simpler power rule for functions. So this is what it says. You take the exponent, you bring it down to the front. So negative 3 will be on the front. You rewrite the quantity. So rewrite 4x plus 5. You subtract 1 from this exponent. So negative 3 minus 1 changes this to negative 4. Now, the chain, you multiply by the link. The link is the derivative of this quantity that is being raised to the power. So the derivative of 4x plus 5 is 4. And you're done. All you can do is clean it up. We can take the negative 3 times the 4, so we can make that negative 12 times 4x plus 5 to the negative 4th. And then last but not least, we don't like to leave negative exponents in our answers, so let's take him back downstairs. We'll keep the negative 12 upstairs and bring 4x plus 5 to the positive 4th power, and that will be our derivative. Okay, 2 to go. Letter D. Y equals quantity 3x plus 2 raised to the 5th power times 6x minus 1 to the 4th power. Now, get ready. This is the first time we're actually seeing 2 sort of major rules hooked up into one problem. What I say to students is, when you look at this problem, what's the overriding rule? Or the rule that's sort of dominating the entire problem? And I hope that you're thinking it's a product. Okay, this is a product. This is like a U times a V. You've got one function times another. So the overriding rule is the product rule. Okay, and then after we identify the overriding rule, I like to look at what is the rule within. What's the rule within that overriding rule? Well, when we run the product rule, we know that throughout it, eventually we'll have to take the derivative of the second and the derivative of the first. And to me, those look like power rule for functions, which we did up top here in letter C, aka chain rule. So we got a lot going on here is basically what I'm trying to say, but we're going to take it one step at a time. So let's start by identifying dy dx, and we're going to run the product rule. So the product rule says in words, you take the first, so I'm going to copy down u, so 3x plus 2 to the 5th power, times the derivative of the second, or v prime. Here comes the rule we just studied today. So we're going to bring the 4 to the front. We're going to rewrite 6x minus 1. We're We're going to drop the exponent by 1 and turn it to a 3. And then we're going to multiply by the length, which is the derivative of 6x minus 1, which is 6. So this part right here is the first times the derivative of the second, or u times v prime. Plus, the second part of the product rule says we take the second, so 6x minus 1 to the fourth, times the derivative of the first. Again, power rule for functions. So 5 comes down to the front. I'm just going to kind of come under here. 5 times 3x plus 2 to the fourth, because we're reducing that by 1, times the derivative of 3x plus 2, which is 3. Whew, that's a lot. Okay, so let's start to see if we can clean this up. So what can we do? Now I'm looking at this plus here. What can we do just on this side of the plus? Let's just look here. Well, we can definitely take the 6 times the 4 and make that 24 in the front. That takes care of the 4 and the 6. These two, we're just going to have to write side by side. 3x plus 2 to the fifth times 6x minus 1 to the third. That's about all we can do on that side. Then we bring our plus down, and now we can kind of look at this side of things. And all we can really do there is take the 3 times the 5, make that 15, that cancels those out, and then 3x plus 2 to the fourth times 6x minus 1 to the fourth, and we'll call that the final answer. So it's messy, but that is the correct answer. Okay, and then our last example, letter E. Y equals this huge quantity to the third power. So my overriding rule, since I have this quantity raised to a power, is going to be the power rule for functions. But the rule within is going to be quotient rule. Because when we do our extra link on the back of the power rule for functions, when we have to multiply on the back by the derivative of the inside of the parentheses, that's a quotient. Okay, so it's going to get a little messy, but here we go. dy dx equals. Okay, the power rule for function says when you have a quantity other than just a single variable being raised to a power, you bring the power to the front. So we'll drop the 3 down. We will rewrite this inside part. We will reduce this by 1. And that sort of just looks like the power rule, basically. But we multiply by the derivative of the inside here. So that's a quotient rule, u over v. So I take the denominator, 4x minus 3, times the derivative of the numerator, which is just 3, minus the numerator, 3x plus 5, times the derivative of the denominator, 4, all over the denominator squared. So this is sort of its own thing going on here. Okay, so what can I do? Well, let's see if we can clean this up. I can't do much here right now, although I'm looking, well, I might be doing something in a minute, but for right now, I'm just going to recopy this as it is. And I'm going to work more on cleaning up this back end by distributing. So I can distribute the 3. So that's going to give me 12x minus 9. And then distributing the 4. This is going to give me 12x, but with the minus, it's going to give me negative 12x. And then this is going to give me 20, but with the minus, it's going to be negative 20. All over 4x minus 3 squared. And then these 12x's will cancel out. So that's going to leave me with negative 29 up top. So dy dx equals 3 times all of this to the second times negative 29 over 4x minus 3 squared. Now, your gut might say, stop there, okay? Your gut might say, done. But what if it's multiple choice and that answer is not there? So let's keep going because we can. What we could do, since this quantity right here is really just being raised to the first power now, I can actually take this 3 in front that's over 1 and multiply the 3 times the negative 29 and then the 1 times the 4x minus 3 squared. So I could do dy dx equals, okay, what's negative 20? What's 29 times 3? Let's see, 27, carry the 2, 87. So we could do negative 87 over 4x minus 3 squared times 3x plus 5 over 4x minus 3 squared. So I'm kind of bringing these two together in the front, multiplying them, and then recopying this guy down here. And then I can go further. When I have this fraction squared, it's the same thing as squaring the top and squaring the bottom and dividing. So I could write it as negative 87 over 4x minus 3 squared times quantity 3x plus 5 squared over quantity 4x minus 3 squared. Then I can multiply these bottoms. So I might write my final answer like this. Negative 87 times 3x plus 5 quantity squared all over 4x minus 3 quantity to the 4th power. So I'm going to add those exponents when I multiply those like bases. And that to me looks like a good answer. Remember, this is just the slope of a tangent line. So I would find it pretty easy to just insert an x there and insert an x there and evaluate this quotient. So there you have it. So we go from easy to medium to more difficult, but these are the two rules we're studying today, and the mastery assignment is going to be attached here in your packet, numbers 1 to 16. So good luck with that.